Okay, my voice is when okay, welcome to this lecture. Today I am going to discuss the performance measures, whatever we had discussed ahead of it. Now, if you remember, we have discussed two important performance measures of the queuing model. The first was the expected number of customers in the system. And now we also discussed expected amount of waiting time in the system. So now there are some remaining performance measures of the queuing model which are expected to be studied by us. So now the next performance measures we are going to compute, and that is the expected amount of the waiting time in queue. The expected amount of waiting time in the system means including the service, and expected amount of the time expected amount of the time waiting time in the queue. So we have a very simple formula. Ws is equal to Wq plus 1 upon mu. 1 upon mu is what? This is the waiting time of this is the service time of single server. This is a service time of a single server. So this is a waiting time. Total time means this is the WS means system. Total time in the system means this is the waiting time and this is the service time. If you want to write here, you can write here. It's service time of an individual customer. So here a simple manipulation in the process. This is Ws minus 1 upon mu. And then this is 1 upon mu minus lambda Ws. We have already computed this value. And this is 1 upon mu. It is service time of an individual. When we simplify it, this comes out to lambda upon mu minus lambda. So W is equal to lambda upon mu minus lambda. And this is known as expected waiting time in the queue per customer. So this is waiting time per customer, expected waiting time per customer. And now we can discuss another fourth one. What is the length of the customers in the queue? Length of the customers in the queue, it means that we are going to apply a little popular formula. This is the LQ is equal to waiting time in the queue is multiplied by the arrival rate. Little's formula. This is known as Little's formula. So lambda, we have substituted the value of this recently computed, just now computed value of this. You have seen this part. So lambda is square upon mu minus lambda. So LQ is equal to, this is the expected number of customers in the queue. Lambda square is equal to mu upon mu minus lambda, and this is known as a expected number of customers in the queue. Now, if we just go ahead, then we have the very important performance measure, and that performance measure is called busy number of servers. How many servers are employed in the system and how many are working or busy? That is a very important aspect for any queuing system. This means that This means that we talk about the busy servers. When we talk about the busy servers means, you look at here, LS minus LQ. LQ means total number of customers in the system, and LS means LQ means total number of customers in the queue, and therefore this part is LS minus LQ is equal to lambda. This part is LS, this part is LQ, and if we ultimately after making the simplification, we get this. Look at here, lambda upon. So number of busy servers is what? C bar is equal to lambda upon mu is equal to rho. So this is equal to customer's congestion. This is known as a customer congestion. It is also known as a load factor. Its another name is load factor. Load factor. This is known as a load factor. This is known as a traffic congestion. This is also known as a traffic congestion. A traffic congestion load factor. Its name is different. Load factor. This is known as a busy servers. Etc. So its name is different, and therefore this is a very important performance measure for evaluating the performance of the queuing system. Now, next one is service utilization. Look here in the service utilization, formula is C bar upon C. Here C is equal to 1. Number of server is 1. So this service utilization is equal to C bar upon 1, and C bar upon 1 means rho. So meaning thereby in the steady state, we are talking about the steady state, because all derivations are computed in the steady state. This happens to be lambda is equal to 4 if we assume, and mu is equal to 5, then lambda upon mu is less than 1, that is the steady state. So if you compute this 4 upon 5, then 0.8 is that is 80%. So service utilization is 80%. We have only one server. So server's energy or time of 80% we are utilized. So owner or manager of the hospital or the service providing center, he may say that 20% time has to be utilized more. But if you look here, the humanity aspect or the individual's facility and convenience, then 20% time is used in the refreshment, in the changing the place from one place to another place for movement, because continuous service is not good, continuous sitting is not good, and also one must have the lunch time. So 20% time is unutilized, means he is getting the time for the lunch, time for the tea, time for the relaxation, etc. So I think this is ideal situation that service is being utilized at 80%. But if it is machine, so 20% time is time may be rechanneled if it is machine. If it is not a human being, he or she. So machine energy of the machine, time of the machine can be utilized. So in this way, this 20% can be utilized. You can say the machine is 20% idle. Means this time may be utilized, may be redirected for another work, another service. Now next is the variance. Variance is what? Variance is the fluctuations in the customers. Fluctuations in the customer means that the abnormal arrival or occurrence of the customers. Abnormal means sometimes is very high, sometimes very low. This kind of the this kind of propensity or property of the arrival is known as a fluctuation. And if we have to study the fluctuation, then we have to study the variance and fluctuation. Why we are going to study the fluctuation? Because the directly or indirectly fluctuation is going to affect the other performance measures, particularly the total time of the system is directly affected by the fluctuation. And if system has the fluctuation, then it is difficult to have the control over the system. And therefore, to study accordingly and to have the control over the system accordingly is the need for the system, and therefore we study the variance so that we can study and we can control, we can analyze and we can control it. So variance formula is this computationally. There are two formulae for the variance. I have already told you in the previous lecture. So we have taken, we have used here this computational part. This is Ex square means En square, and Ex means this is mean whole of the mean, or Ex square. This is whole of the mean. So this is as usual in square Pn, and rho 1 minus 4. This is the value of expected n. And when we try to simplify it, slowly and slowly we come to this point. So rho upon 1 minus rho square, it is equal to variance n is equal to rho upon 1 minus rho square. This is fluctuation of the customer. So you can convert this formula in terms of lambda and mu too, and simply putting the value of lambda and mu, we can compute the value of variance. Total cost of the system, as I have already explained that total cost is very important, and without the analysis of the cost, without knowing the factor of the cost, it is very difficult to sustain, to survive any system. And therefore, if we want to survive efficiently any system, we need to study the cost system, that is the total cost system. We have also discussed about it that in isolation or we cannot separately study the waiting cost and service cost, and therefore we study the total cost. So total cost, TC is what? TC is waiting cost plus service cost plus C1 and C2 per unit costs of waiting and service cost respectively. Then TC is equal to C1 expected n plus C2 mu, and this is, if it is this is total number of customers in the system. So if one customer is charged C1, then multiply this with total waiting cost. This is the rate per unit. This much this much of customers are being serviced. So C2 into mu is equal to, this is service cost, and therefore C2 and mu, this form this aspect of the cost. Under steady state, let C1 is equal to 10, C2 is equal to 12 units as per the units. We have not mentioned here because this may be 1,000, maybe dollar, maybe 100, per unit, maybe whatever it is. So therefore there is no unit you look at here without units. So lambda is 4, mu is equal to 6 in the steady state. So Tc is equal to 10 into 4 upon 6 minus 4 plus 12 into 6, 20 plus 72, this is 92 unit size per requirement. So Tc is equal to 92. This is total cost of this system. Since we are mathematicians, so here, what is happening? We can optimize this TC. TC is what? TC is involving, this is a function of lambda and mu. C1, C2 are constants. So as a mathematicians, we can optimize this C1 and C2 means with the help of the simple mathematics, we can talk about the optimization, two types of optimization. One is with respect to lambda, another is with respect to mu, and another is what? With respect to lambda and mu. So when we talk about the optimization, it means that with respect to lambda, we can optimize. With respect to mu, we can optimize. With respect to both, we can optimize. If we optimize with respect to lambda, we will find one nonlinear equation. We will solve it by applying certain given procedure, and we can apply the computing process to find it. And similarly, we can do with respect to mu. Similarly, with respect to lambda and mu, then this first derivative has to be 0. Second derivative has to be optimum according to cost is minimum. So this must be positive. This must be positive. This will provide us a system of nonlinear equation. If this gives us system of nonlinear equation, this has to be solved with the help of the computing, and we will get the answer. So this is a part of research or the project. You need not concern here. Example, you look at to make the concept quite clear. This example is very important. Look at this is simply a model. I mean, we need not bother about the numbers. Numbers may be very smaller. The computational process may be very simple, but this problem may be understood for generalizing the bigger problems. So look at how we can apply the concept of the queen theory to modernize, to efficiently or nicely managing the queuing system. Because we provide the tools, we provide the knowledge as a tools to the manager, to the owner, so that they can improve their system in the interest of society and in the interest of the service providing system. We are not manager to change it. Just we are expert to provide the feedback. A small but good hospital is working with a single neurosurgeon. Okay, only one doctor is here. This is a small but very good hospital. Neuro patients arrive at hospital according to Poisson distribution with a mean of 4 patients per hour. This is arrival or occurrence of the arrival is given here, and this follows the Poisson distribution. There is only one neurosurgeon. Neuro patients are coming to the hospital. Okay. Parand may wait in the waiting room. May wait in the waiting room. They have options or of the hospital or in the park nearby the hospital if surgeon is busy with patient. Means we do not know that what should be the size of the waiting space or waiting room. So if waiting room is full, then in the slide there is a park, so patients go there and they sit down. Now the owner of the hospital wants to know what should be the optimum waiting space or waiting room, optimum size waiting room, optimum space waiting room, which he should provide to the service providing or medical means this medical service providing system. So let us try to understand with the help of the queue. The time for treatment of a patient is exponential here with a mean of 10 minutes. Means in 10 minutes one patient is being treated. Here there is a bind, here is binding on system capacity, there is no binding. There is no binding on system's capacity or size, keeping in mind the practicality of this purpose. So whosoever comes from wherever the patient comes, they can join this hospital, and therefore capacity is infinity because we are studying the system of infinity. And source population is also infinity. In such a situation, the owner of the hospital wants to determine the capacity. As I told you, capacity or waiting space of the hall of the hospital. So how we can approach this kind of problem? So just to look here. From the statement of the example, we can have lambda is equal to 4, mu is equal to in 10 minutes 1, therefore in 60 minutes 6, or so mu is equal to rho is equal to 4 upon 6, that is 2 upon 3 is less than 1. This is the steady state equation. We compute LQ and LS here. LQ by the formula that comes out 1.33, and similarly the LS comes out 2. That is only one server is here, meaning thereby we are going to add one service, that is one person is being serviced, so 1 plus 1. 2 means how this has come, 1 plus 1. This is 1 plus 1. This is 1 plus 1. So from LQ and LS, as a ordinary user of the queuing theory or the analyst of the queuing theory, we can immediately come to the remark that since LQ is what? LQ is the expected number of size of the customer, expected number of customers in the system and in the queue, and therefore this size or this size must be recommended for the waiting space. This is one way. So 2 and more than 2. You look at here, 2 or more spaces must be required for the hospital as a waiting space. But from another point of view, to become some more practical or just to face some more realistic situation, how can we handle the same thing in more practical and realistic manner? What we can think more practically, how we can think as a practical man. An arriving patient at the hospital should find the waiting space at least 90% of time. Meaning thereby, one way of thinking is that if I am arriving patient, then the hospital is good if 90% of the time the arriving patient gets the waiting space. And I mean there is no problem in the waiting space. Immediately she or he gets the waiting room. 90% is okay. This is the practical situation. You can say it may be 99%. This will become very, very idealistic. If somebody say 85%, it is also okay. Somebody say it is 95%, it is also okay. So this, if you vary it, the problem will be giving you different solutions. Look here. This is known as practical statement. This is a practical statement. Realistic statement means it is very close to reality. I am not just only solving the problem from the theoretical point of view, rather we are solving the problem from the practical point of view by applying the knowledge of Q. Now MM1 GD infinity model. Q means MM1 GD infinity. Now, practical statement may be mathematically and equivalently expressed. You look here. This is total probability, total for P1, P2, P3 up to, oh, okay. Yes, perhaps yes is not explained here. Yes, what is yes? Let S be waiting room or space for patients at hospital. What is S plus 1? Then S plus 1. B spaces in the system, including service space. One patient is in service, so yes plus 1. Okay, so from the practical statement, the sum of total probabilities, that is this one, is greater than equal to 90%, or 90% of the time means this probability must be 0.90 at least, means greater than equal. You must be agreeing with us. So whatever practical statement we have given, this is the corresponding or equivalent mathematical statement. Okay, but this probability is computed by the same formula of the Pn derived from MM1 model. This is not the probability taken from outside. So this, we are within the range of knowledge of model, given model. Okay, it is 90%. So if it is 90%, so compute the P naught. Pn is given here. You must be knowing this formula. This is very popular formula. We derived yesterday. So we compute here P naught. If we compute P naught, I am just, for you, I am giving this value. This is P naught means P naught rho, sorry. P naught means this is rho naught, N is not. So this is 1, 1 minus rho. So 1 minus lambda upon mu means 1, 2 by 3. This is 2 by 3, 4 and 6. The same example, 4 and 6. And 1 by 3. So this is 0.333, this probability. And the cumulative probability, another column is this one. We compute the P1, then we get 0.22, and by the same formula, and similarly, the cumulative probability means sum of this and sum of this is equal to this cumulative. Similarly, P2, sum of this and sum of this and this. P3, P4, P5. You just look where you are going 90% or more. 86 is less than 90% or 0.90, 91, 0.91, this is more. So this condition satisfies the condition of the mathematical statement, and therefore P5, this is P5 has become more than 0. This according to more than, this is 9, this is not 5, this is 9. So according to our practical statement, next to be this condition is satisfied, we can say. So n is greater than, or n is greater than this, n is means 5. So meaning thereby s is what? S is 5. You can compute here 6 here, 7 here, so forth, so on. But yes, this is waiting space is more than 5. At least 5. So if you are suffering, if you have no sufficient amount of fund, so at least 5 waiting spaces you have to construct, you have to tell. If you are earning service provider, then you have to make more than 5. But at least 5, you can make it 6, 7, 8, 9, 10, etc. So minimum is 5. You just look here. Earlier was 2 by LS and LQ. No, that was not the optimum, because that was the LS and LQ. You expect it that 2 customers are coming per day, but that is not the optimum one. So optimum way of calculating The waiting space or the number of customers which may come on any day. So this someday they may come at least 5, more than this. So as another way we can also compute this. Here is the one solution, another solution, similar solution. Lambda, this sum over Pn, you have known this, you have known this. Here is the yes, this is yes is greater than this one, and you by the geometric rule, this sum geometric series, this is a sum is equal to this. So this cancels this. 1 minus rho to the power s plus 1 is this. This implies you multiply by minus in both sides. This inequality will be changed, and this side will be rho s plus 1 is this. Rho s plus 1 is less than equal to 0.1. And look here. And you take the log. If you take the log s plus 1, log rho is greater than equal to log 0.1. Here you may be asking that why this inequality we have changed. So reason is, you look here, log x is less than 0 for the value lying between 0 and 1. So we are taking the log what? We are taking the log 0.1. So this changes the inequality. This is the reason this changes the inequality. So yes, s plus 1 is greater than log 0.1, log rho s is greater than log 0.1, and log 2.2 upon 3, 4 by 6 is 2 by 3, and this one has come this side, minus 1, so s is greater than 4.679, that is equivalent to 5. So waiting space is what? S is greater than equal to 5. So another way of computing the 5. So this is a technical problem which can be approached with the help of the queuing theory, and queuing theory, the particular model MM1, ZD infinity and infinity. So from both of the way we can come to the conclusion that therefore this figure is much more than an inspection view of LQ and LS, which was 1 or 2. Inspection view means waiting line, how much persons come, 5 persons or 2 persons come, you say tomorrow will also come, 2 persons. No. That is not the optimum. Optimum is you can predict this, but this is better way. So if you are conducting any case study, this is the good way of solving the problem. That depends. This is the theoretical outlook. You look here. This is the theoretical outlook. Though queuing theory is practical, dealing with the practical aspect, but this is the theoretical. This is the theoretical outlook. This is the theoretical outlook. But this part is practical, quite practical outlook. This is the practical outlook. And we are applying the queuing theory, nothing less or nothing more. So therefore, above result, this is more close to reality of situation. This one. And it is therefore an optimal solution for the given situation. So in this way, practical way, a problem is solved with the help of the queuing problem is solved with the help of the performance measures and concept of the Pn, a derivation of a main derivation of MM1 GD infinity and infinity. In this way, now it is enough. Today I am going to open it for discussion. If you have any